So the last idea we want to look at is this idea of conditional probability. So finding the probability of something, if we already know something has happened, we already know something about the problem. Find the probability of an event A given that B has already happened. And there's a formula for it. Probability of A, and then we just use a vertical bar there, and that just means given that B has already happened, would be the probability of A intersection B divided by the probability of B. In other words, the probability of A and B happening over the probability of B. Or if we prefer, we're just counting the number of objects in that set of A intersection B divided by the number of objects in the set B. What that means is this: if the probability of A given B is the same as the probability of A, then they're independent events, because the fact that B has already happened was irrelevant. The probability of A didn't change. Or we could play around with that formula there and say, well, another way of working out whether they're independent is to have a look at the probability of A intersection B, and if that's the same as the probability of A times the probability of B, then they're independent events. Let's look at this. We've got a mixed language class. They either study French, Latin or Japanese. The number of students who study each language, and we've got a Venn diagram displaying all that information. We want to know the probability that a student who studies Japanese also studies French. So essentially what we're saying is, what's the probability they study French given that they study Japanese? So we know they study Japanese. But with a Venn diagram, I can look at it and say, well, really Japanese then becomes the universal set. And I'm just looking at those objects, and how many of those objects also had French? Well, there was 2 here and 1 here. So 3 out of 10 objects altogether. We've got 2 boxes. Each box has got 4 stones in it. But the first box, 4 black stones. The second box has got 2 black and 2 white stones. We're going to choose a box at random, then pull a stone out of that box. We want to know the probability that that stone is black. So first of all, I'm going to pull a box, and let's say it's box 1 I get. There's a 1 in 2 chance that I pull out box 1. But if I do, I know that they have to be 4 black stones, so it's got to be a black. So it's just a probability of half. However, if I pull out box 2, so the other possibility, 1 in 2 chance of getting box 2, but there's a 2 in 4 chance that I pull out a black one for that. 3/4 is our probability. The other way I could have done this question is simply go, well, really, because I'm randomly picking the box, then does it really matter that it's equally likely the boxes? So I could have just said, look, there's 8 stones altogether. I'm just going to get one of those stones, and there's a 6 in 8 chance, 3 and 4. Okay. But now, if I turn it into a conditional probability, it's not known which box the stone's been drawn from. However, we know we pull out a black one. What's the probability that it came from box 1? So we're saying, what's the probability it came from box 1 given that the stone we got was black? Well, that would be the probability of being black and came from box 1 divided by the probability of black. So a half times 1 divided by 3/4, a 2 in 3 chance. So in a school, 55% male students, 45% female. Now the male students, 13% of them say Monday's their favourite day of the week. However, with the females, 18% say Monday's their favourite day of the week. Find the probability that a student chosen at random is a male whose favourite day is Monday. What's the chance of that? So we know probability of male, 0.55. Probability that they think Monday's their favourite day, given that they're male, is 0.13. So then, there's our formula. But we're trying to find the probability that a chosen student is male and their favourite day is Monday. So actually the top of the fraction. But we know these other 2. So we'll substitute those numbers in, rearrange it, and we get our probability. So probability of male and Monday, 0.0715. Let's have a look at this HSC question. We've got 3 6-sided dice, but they're not normal dice. Well, the first one, well, 2 of them are normal, 1, 2, 3, 4, 5, 6. But the third one, the faces on the die go 1, 2, 3, 5, 5, 5. We're going to randomly pull out one of them and then roll it. What's the probability we get a 5? Probability we get a 5. Well, first of all, there's a 2 in 3 chance I get one of the normal die. and then there'll be a 1 in 6 chance I roll a 5. Or the other thing that could happen, there's a 1 in 3 chance I get the special die, but on that one, there's a 1 in 2 chance of rolling a 5. 5 out of 18. But given that the die shows a 5, what's the probability that it was the special die that we pulled out? Probability of special die, given that it rolled a 5, would be special die and roll 5 divided by just the probability of a 5. Subbing that in, we get 3/5. There's another way I could have done that. If I look at the 3 die, but I'm only interested in 5s, because we know it's going to be a 5. As far as we're concerned, die 1 just has 1 5, die 2 has 5, and the special die has 3. That's really all we're considering here. Well, the probability then that special die, given that it's 5, well, they've all got 5, all up, 3 of those 5s are on the special die out of, there's 5 5s all up. So 3 in 5. Well, that's a way of using diagrams to solve that problem. 12G. Wow.